All right. Thanks for the introduction. So let me start by talking about the background of the whole project. So the idea is that there are a lot of road maintenance texts around. These can include design documents, log, inspection reports, a lot of unstructured natural language data. And there are a lot of applications that we want to use these data for. So in our research group, the specific application is the creation of a road digital twin, which essentially is like a digital copy of the road network that encompasses all data related to road maintenance that we might need. And to create this road digital twin, we have a set of data requirements that we need to adhere to. And to satisfy these requirements, one way to do it is to classify them into structured data. These can include defect categorization, maintenance action, and asset information. So large language models, I'm sure you're all aware, is a very powerful way of classifying these texts now. They were trained on general domain texts to have task agnostic knowledge. But there is a difficulty in applying them in road maintenance applications because road maintenance applications, like other engineering applications, are very domain specific. The vocabularies are different, tasks are different. So general domain knowledge might not apply. Additionally, there are the tasks might be very complex. They might have a lot of classes. For example, instead of classifying a text into whether or not it's happy or sad, we're classifying it into one of, say, 100 defects. So it's much more complex than the tasks that we're usually seeing like when you're pre-training these large language models. There's also a lack of label data for these engineering applications, and so it's hard to curate data set to fine-tune these LLMs to a specific task. So we first want to look at what architectures there are that leverages LLMs to classify text. So LLM text classifiers, there are a few types. So one way of using them to classify text is through fine-tuning them traditionally. So what that does is you add an initialized classification head on top of an LLM, which have parameters that you have to train for to output a single class prediction. And these techniques usually require a lot more training data, so they're kind of more data hungry. But if you want to look at more techniques that are more tailored for data scarce applications, then there are data efficient methods out there. And one of them is called SetFit, which stands for Sentence Transformer Fine Tuning, which basically leverages a small LLM, or some people call it a PLM, a pre-trained language model, called Sentence BERT, that can basically use a specialized architecture and training regime to fine-tune these models to output a prediction with very few examples per class. And the third way of using these LLMs to classify text is through context learning, which is also very popular. How it works is you literally put through a natural language prompt to tell the model what to do and tell it to output prediction. So in our project, we do not consider context learning as a viable alternative because, as I said just now, the task is very complex. There are many different classes out there. So to do context learning, you have to put everything in a single prompt. And having so many classes, say 100 classes, the difficulty is that it might exceed the maximum context window for the model, so it might not be able to handle all the classes at the same time. And even if the context window is large enough, it might suffer from context overload and it might give very inconsistent results. And also using context learning requires much bigger, much more powerful models that require a lot more computational power. And for a deterministic task like text classification, it might not be very justifiable to use such a big model for it. And these models are often closed source, which means that it might not be the best idea to put through sensitive government data like road maintenance data through them. So that's why we don't consider in-context learning as a viable alternative. So this project basically compares traditional fine-tuning and SetFit on classifying road maintenance text in a data vision setting. So to create the data set, we took data from New York City Open Data in this dataset called Street Construction Inspections and Corrective Action Requests. The first step that we did was to remove duplications and also remove rare classes so that we can ensure that there's sufficient evaluation data available. And after we clean the data set, we create different simulated few-shot data sets to simulate cases of data scarcity. And so we basically randomly subsample this data to form training and validation data sets where there are n examples per class and use the rest as testing data. The whole data set has roughly like 400,000 texts, I think. So the task is kind of like this. So you have a road inspection text like, which in our case, it describes an instance of a road code violation in a construction, in a roadwork construction. And there are one of 83 road codes that can be violated. So it's a classification task of classifying a text into one of 83 classes. So a lot of classes traditional models might struggle with. And we tested by classifying the text using both traditionally fine-tuned LLMs and also using SetFit. And we fine-tune these models using 1, 2, 3, 4, 5, and 10 examples per class. So here are some of the results. So these two rows are different examples of a inspection text being classified. So on the left, the column is the actual road inspection comment. And then the second column is the prediction. The third column is the correct example. So the first row is a correct prediction. The second row is an incorrect one. But if you look at the description of the classes, you can see that they're very specific. They're not as simple as, in sentiment analysis, where it's like happy or sad. It's much more abstract and complex. So these are some of the results of the analysis of the So one interesting observation is that SetFit performs much better than 7 billion parameter LLMs that were fine-tuned traditionally. Bear in mind that SetFit uses a sentence transformer that only has roughly 300 million parameters, so more than 20 times smaller than the 7 billion parameter LLMs. So, for example, when being trained with one example per class, SetFit achieves an accuracy score of 30%, which is not great, but is much better than competing LLMs that were fine-tuned traditionally. And what it says is like, maybe the way you use the model is more important than how big the model is. So this is actually a very interesting insight. And because these two models they vary a lot in size. So what if we compare it to SetFit to other models that are comparable to it in size? So we compare SetFit to other LLMs or PLMs that have roughly 100 million parameters. So the same order of magnitude as the base model inside SetFit. And interestingly enough, the SetFit still beats the other traditionally fine-tuned models, but the performance is actually not that different compared to last time, which suggests that model parameter size does not actually significant. It's not the bottleneck for these traditionally fine-tuned LLMs in low resource settings. The one potential bottleneck is the uninitialized classification head, which requires a lot of training data to prepare. So because there are 83 classes, it's also interesting to look at the performance across different classes, because for road maintenance applications, we want reliability. And having classes which perform poorly is not ideal. So there are actually some classes that have really high effluent scores, like almost 1. And there are also classes which have really low effluent scores. And I think what this says is that the absolute performance for certain classes are still low. So there's still a lot more work to be done to adapt these LLMs to fully take over a classification task for road maintenance text. And these are, so in conclusion, so the insights are that LLMs offer new ways of classifying text by leveraging pre-training. However, general domain pre-training do not automatically apply to domain-specific text. So this is due to the difference in vocabulary, the complexity of the task, etc. And dedicated few-shot techniques such as SetFit improves over traditionally fine-tuning state-of-the-art large language models. However, even using dedicated low-resource techniques, the absolute performance is still low, that it might not there's still a lot of work to be done to adapt them for technical road maintenance text applications. So future direction, as I said just now, an interesting insight is that model parameter isn't really the limit, it's how you use the model that's the limit. So we can potentially explore new domain-specific, new pipelines that can better leverage domain-specific knowledge to supplement the lack of training data so that we can adapt these models without having more labeled data. For example, in a RAG style pipeline, RAG standing for retrieval augmented generation. So leveraging sources of domain knowledge such as design, like for example, like legal documents. Another thing to explore is different classifier architectures that can maximize pre-training knowledge inspired by techniques such as SetFit, which exactly does this. So yeah, in conclusion, these are our sponsors, and yeah, these are so feel free to connect with us.